Now we are going to see about capacitors and capacitance. So generally capacitor is a device for storing electric charge and hence electric energy. So it consists of two conductors separated by a insulating medium. It can be air or any other medium between the two conductors. Then that is called as a capacitor. And the capacitance, it is defined as the rate of charge on one of the conductors, any one of the conductors, to the potential difference between the two conductors. So it is denoted by C and the unit is farad. So general formula, standard formula is capacitance C is equal to Q by V, where Q is the charge on any one of the plate and V is the potential difference between the two conductors. Next, different examples of capacitors are as follows. What are the different examples of capacitor? Is parallel plate capacitor, coaxial capacitor, spherical capacitor, multiple dielectric capacitors, and capacitance of an infinite length wire. So first one is capacitance of a parallel plate capacitor. So what is meant by parallel plate capacitor? That means two plates, right? Assume this is one plate, okay, sheet or plate, and this is one more sheet or plate. So these two are separated by a very small distance. Say the distance between these two is represented by d. Assume these two plates are parallel to any one of the axes, either x-axis or y-axis or z-axis. In this case we are assuming these two are along the x-axis and these two plates are separated by a distance d. Okay, so here it is mentioned very clearly capacitance parallel plate 1, parallel plate 2, plate 1, plate 2, and plate 1 charge is q and plate 2 the charge is negative. These two plates are separated by a distance d. So consider a parallel plate capacitor with the plate separated by a distance d, and the area of this is, that is the gap between these two plates, is a meter square. So Q be the charge on the any one of the plate. Then surface charge density rho s is given by rho s is equal to Q by A. Why the surface charge density is defined as in this case? Because the plate is considered as a sheet. For a sheet, we have to define the surface charge density. So therefore, we are defining surface charge density for this concept. So rho s is equal to Q by A. Then the electric field intensity of a sheet of charge, that what we have discussed in module 1. So E bar is equal to rho s divided by epsilon AR bar. It is a standard formula. Now the same formula is applicable for this concept, that is parallel plate capacitor. Parallel plates are placed along the x-axis, so therefore AR bar is replaced by AX bar. So therefore E bar is equal to rho s divided by epsilon AX bar. And the standard potential difference, that what you have discussed in module 2. So V is equal to minus integration, that is line integration of E bar dot dl. E bar is called as a electric field intensity, dl is called as a differential length. So V is called as a electric potential. So V is equal to minus line integral of E bar dot dl. So E bar is this, that is rho s divided by epsilon, rho s divided by epsilon AX bar. Now the potential difference across the plates is given by V is equal to minus line integral of E bar dot dl. What is dl in this case? Because we consider these two plates along the z-axis, so therefore dl is equal to dx ax bar plus dy ay bar plus dz az bar. So take the dot product of these two, that is E bar dot dl, then you will get E bar dot dl is equal to rho s epsilon into dx. The next is we need to substitute in the formula, that is V is equal to minus integration, where the limits are changing from 0 to d, because the distance between the two parallel plate capacitor in this case is d meters from d to 0. So therefore minus integration d to 0 rho s divided by epsilon dx, that what you got from the previous equation. Finally you will get V is equal to rho s d divided by epsilon. We know rho s is equal to Q by A. Substitute here, then you will get the voltage is equal to, that is potential difference is equal to Q divided by A epsilon. The capacitance defined as C is equal to Q by V. So substitute V here. Finally, we will get capacitance C is equal to epsilon A by D farads. It is a standard mathematical equation that what you have studied also of a parallel plate capacitor. C is equal to epsilon A by D. Next one is capacitance of a coaxial cable, right? So general cable is, right, that what we have seen. Assume this is the cable. For this cable we need to determine the capacitance expression. Okay, so let's see here how to define and how to get the expression of capacitance for this coaxial cable. So first we need to consider the coaxial cable of length L meters and having the inner diameter A meters and outer diameter is the B meters. Length is L, inner diameter A, outer diameter is B. So that what you have the sentences are mentioned here. And in this case we have to define rho L. In the previous case we defined what? Rho S. Okay. Why you have to define as a rho L means this coaxial cable is called as a line conductor. For line conductor what we have to define is rho L. Rho L is equal to Q divided by L, or Q is equal to rho L into L. It is a standard mathematical equation from module 1. So electric field intensity of a coaxial cable is like a line conductor only. So for line conductor E bar is equal to rho L divided by 2 pi epsilon R into A R bar. Okay now let's see the potential difference between the inner and outer radius of the conductor is V is equal to minus integration will change from B to A, that is outer diameter, value to the lower radius B to A, E bar dot dl. In this case we know dl is equal to dr into ar bar. Why it is dr into ar bar is cable is like a cylindrical shape, so therefore in cylindrical coordinates dl is dr ar bar plus r d phi a phi bar plus dz az bar. So in this case we are considering along the r direction only, so therefore the remaining two terms are not considered here, that is a phi bar as well as az bar. So dl is equal to dr into ar bar. E bar is equal to this and dl is equal to this. Take the dot product, you will get the E bar dot dl and substitute this one in the voltage potential difference equation. V is equal to minus integration B to A E bar dot dl. Finally, you will get the voltage expression. Voltage V is equal to rho L divided by 2 pi epsilon ln of B by A. And we know that rho L is equal to Q by L. Substitute here. Finally, you will get V is equal to Q by 2 pi epsilon L into ln of B by A. So therefore capacitance is equal to Q by V. Substitute V here, you will get 2 pi epsilon L by ln of B by A. If you want to determine capacitance per unit length, then that is called C by L. Then bring this L this side. Finally capacitance C is equal to 2 pi epsilon ln of B by A. So this is about coaxial cable of capacitance of a coaxial cable. In the same way we can determine spherical capacitor also. Capacitance of a spherical capacitor. So spherical example is the globe shape. Assume the object in the globe shape. So that is also once again having the two radius. One is inner radius A, another one is outer radius B. Inner radius is having a positive charge and outer radius is having the negative charge. Now in this case the name itself is saying spherical capacitor, so therefore we need to consider spherical coordinates. So same mathematical equation, E bar is equal to Q divided by 4 pi epsilon R square into A bar. Spherical in this case looks like a point only, so therefore electric field intensity is Q divided by 4 pi epsilon R square into A bar. Previous case is cable. Cable is a line conductor. So for line conductor, E bar is equal to rho L divided by 2 pi epsilon R into A r bar. So that depending on the shape of the object, we need to write the formula. So then once again potential difference V is equal to minus integration A to B E bar dot dl. So dl is equal to once again in any either cylindrical or spherical, because it is only along the r direction only, dr into ar bar. So therefore E bar dot dl is equal to this V is equal to, once again substitute in this mathematical equation, then you will get the V. From the V you can determine that capacitance C is equal to Q by A. This V you substitute here, we'll get the capacitance of a spherical shell. This is about the capacitance of a spherical cell. Similarly, in the same way, multiple dielectric capacitors. Multiple dielectric capacitors means that there will be many number of layers, dielectric mediums. Epsilon, dielectric medium 1 is represented by epsilon 1, dielectric medium 2 is represented by epsilon 2. Area of the object is A only. So, next, the capacitance is epsilon A by D. It is a standard mathematical equation that what you have discussed for the parallel plate capacitor. There are multiple layers, so therefore here the distance D is separated like D1 by epsilon 1 plus D2 by epsilon 2 and so on. Then finally equivalent capacitance is CEQ is equal to 1 by d1 by epsilon s plus d2 by epsilon s, where s is called as a area of the parallel plate. So this is about the capacitance of a multiple dielectrics. This is about completely capacitance of all the examples: parallel plate, coaxial cable, spherical shell, as well as multi dielectric mediums. Okay, thank you.